Look angle determination. In satellite communication, radar systems, and tracking applications, look angles refer to the orientation angles of a ground-based antenna or sensor needed to establish a line of sight connection to a satellite or target in space. Look angles consist of the azimuth angle and the elevation angle, which are calculated based on the relative positions of the observer and the satellite in a three-dimensional coordinate system. Key definitions: azimuth angle, R, the horizontal angle measured clockwise from true north to the projection of the line of sight, loss, vector onto the ground plane. Elevation angle, E, the vertical angle between the local horizon plane and the loss vector pointing toward the satellite. Line of sight, loss, the direct vector connecting the observer, ground station, and the satellite. Coordinate systems for look angle determination. To calculate look angles, two primary coordinate systems are used: geocentric equatorial coordinate system, a 3D Cartesian coordinate system centered at the Earth's center. Satellite position is given in terms of x, y, z, x, y, z. Topocentric horizon coordinate system, a local 3D system centered at the observer's location with axes defined as east, x-axis, north, y-axis, upward, zenith, z-axis. The goal of look angle determination is to transform satellite position from the geocentric system to the topocentric horizon system, then extract azimuth and elevation angles. Inputs for look angle calculation: observer's geodetic coordinates, latitude, phi, longitude, lambda, altitude, hh, above the reference ellipsoid. Satellite position, provided in the Earth-centered inertial, ECI, or Earth-centered Earth-fixed, ECEF, coordinate system. Earth geometry, WGS-84 reference ellipsoid is often used to account for the Earth's non-spherical shape. Time reference, accurate time, UTC, is critical to compute the satellite's position since it changes dynamically with orbit propagation. Step-by-step look angle calculation. Step 1. Satellite position in ECEF coordinates using orbital mechanics or two-line element, TLE, data. Propagate the satellite's position in the Earth-centered inertial, ECI, frame. Convert the position to the Earth-centered Earth-fixed, ECEF, frame using RECEF equals RZ, theta G, Reci, Math BF, R, underscore, text, ECEF, equals, Math BF, R, underscore Z, theta underscore G, Math BF, R, underscore, text, ECI, where, theta G, theta underscore G, Greenwich Mean Sidereal Time, GMST, angle at the given time. RZ, Math BF, R, underscore Z, rotation matrix about the Z-axis to account for Earth's rotation. Step 2. Observer's position in ECEF coordinates. Convert the observer's geodetic coordinates, phi, lambda, h, to ECEF coordinates. XO equals n plus h, cos phi cos lambda yo equals n plus h, cos phi sin lambda zo equals n, 1 minus e2, plus h, sin phi. Begin, aligned, x underscore o and equals n plus h, cos phi cos lambda y underscore o and equals n plus h, cos phi sin lambda z underscore o and equals left, n, 1 e squared, plus h, right, sin phi, end, aligned, where nn equals radius of curvature of the ellipsoid at latitude phi, n equals a1 minus e2 sin 2 phi, n equals frac sqrt 1 e squared sin squared phi r, semi-major axis of the Earth. Eccentricity of the Earth. This gives the observer's position in ECEF coordinates, xo, yo, zo, x underscore o, y underscore o, z underscore o. Step 3. Loss vector in ECEF coordinates. The line of sight, loss, vector from the observer to the satellite is RLOS equals RS minus rho, Math BF, R, underscore, text, loss, equals, Math BF, R, underscore S, Math BF, R, underscore O, where, RS equals, XS, ES, ZS, Math BF, R, underscore S equals, X underscore S, Y underscore S, Z underscore S, satellite position. Rho equals, XO, yo, zo, Math BF, R, underscore O equals, X underscore O, Y underscore O, Z_O, observer position. Step 4. Transform loss vector to topocentric horizon system to determine azimuth and elevation angles. Rotate the loss vector from the ECEF frame to the topocentric horizon frame. R topo equals recef right pointing arrow topocentric R loss, math BF, R, underscore, text, topo, equals, math BF, R, underscore, text, ECEF right pointing arrow topocentric. Math BF, R, underscore, text, loss, the rotation matrix is, recef right pointing arrow topocentric equals, minus sin lambda cos lambda 0 minus sin phi cos lambda minus sin phi cos phi cos lambda cos phi sin lambda sin phi, math BF, R, underscore, text, ECEF right pointing arrow topocentric, equals, begin, B matrix, sin, lambda and cos, lambda and 0, sin, phi, cos, lambda and sin, phi, lambda and cos, phi, cos, lambda and cos, phi, sin, lambda and sin, phi, end, B matrix, the resulting vector R topo equals, E, N, U, math BF, R, underscore, text, topo, equals, E, N, U, represents the loss vector in the topocentric frame, E, east component. NN, north component UU, up, zenith, component step 5, compute azimuth and elevation angles from the topocentric loss components. Elevation angle, E equals arcsine, UE2 plus N2 plus U2, E equals, arcsine, left, frac, U, SQRT, E squared plus N squared plus U squared. Right, azimuth angle, R, or equals arctan 2, E, N, A equals arctan 2, E, N. R is measured clockwise from true north. Adjust the angle to ensure it lies in the range, 0 ring operator, 360 ring operator, 0 caret, circ, 360 caret, circ. Accuracy considerations. Earth oblateness. The Earth's equatorial bulge affects satellite position, especially for near equatorial orbits. Atmospheric refraction. At low elevation angles, atmospheric refraction bends the signal path. Apply correction models to improve accuracy. Orbital perturbations. Satellite position must account for gravitational perturbations, solar radiation pressure, and atmospheric drag. Timing accuracy. Accurate time synchronization, e.g., UTC, is essential for real-time calculations. Applications. Ground station antenna pointing. Align antennas for GEO, LEO, or MEO satellite tracking. Radar systems. Point radars at moving targets or space debris. Telecommunications. Ensure line-of-sight signal transmission for satellite communications. Astronomical observations. Track celestial objects with ground-based telescopes. Conclusion. The determination of look angles, azimuth and elevation, is critical for accurately pointing ground-based antennas or sensors towards satellites or targets in space. The process involves transforming satellite and observer positions from global geocentric coordinate systems to a local topocentric horizon frame. By calculating the line of sight vector and applying trigonometric relationships, the azimuth and elevation angles are derived. Precision in look angle determination depends on factors such as Earth's geometry, atmospheric refraction, orbital perturbations, and accurate time synchronization. These calculations enable reliable communication, tracking, and observation in satellite systems, radar applications, and astronomical operations. Closing the YouTube video. Alright, that wraps up our deep dive into look angle determination. We've covered the concepts, calculations, and the importance of accurately pointing antennas for satellite communication and tracking. If you found this video helpful, don't forget to like, subscribe, and hit that notification bell so you won't miss more in-depth content like this. Have questions or want me to cover a specific topic next? Drop a comment below. Thanks for watching, and I'll see you in the next video. Keep reaching for the skies.